Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we're going to work through the notes of binomial expansion. So this is a lesson that I previously taught with my students, and what I'm going to do is I'm just going to go back through the lesson, kind of explain the way that I taught it, and also provide the answers so you, as well as my students, have a way to kind of check the work and kind of, go back and review it. So let's go ahead and get started. All right, now binomial expansion is, day 2 in our polynomials unit. We're going to learn how to expand a binomial. We're going to learn how to determine any element within binomial expansion, and we're going to learn how to create a binomial squared. So I started this off by just letting students say, all right, let's just practice kind of multiplying, multiplying, expanding binomials. It's really kind of more of an algebra 1, algebra 2 kind of task, but I wanted students to just kind of get some practice with that. So, anything raised to the 0 power is just going to be 1. When I have x plus 1 squared, anything raised to itself, it's just going to be, x plus y. And then the really important thing that I wanted to remind students is remember that x plus y squared does not equal x squared plus y squared. That is one of the initial first mistakes, again, students make. Remember, that is x plus y times x plus y. So therefore, what the students need to do is we need to do distributive property, or, a lot of times students remember from binomials, remembering FOIL or box method or whatever kind of method you might have used. So therefore, we would get x squared plus xy plus yx plus y squared. Now, it's really important to recognize in this case that even though x, y, and yx are not in the same order, they are like terms. They have the same base, x, and they both contain an x and y to the power of 1. So those are like terms, and we can just write them in really any order that we want to. Just like that is fine. Now, x plus y cubed is x plus y times x plus y plus x plus y. But since I'm into one that doesn't want to do as much work, or try to do things a little bit faster, what I'm going to do is I'm going to write it like this: x plus y times x plus y squared. And the reason we're going to write it like that is because, one, even if I didn't know what x plus y squared already was, I can typically do that really quickly in my head because I've multiplied binomials so fast or so many times, and I'm hoping that would be the same thing for you. So by writing this as a binomial times a binomial squared, I can kind of quickly do this, and then I'm going to have to multiply out, which again is going to take some work. So I know x plus y squared, so I'm just going to rewrite this as x plus y times, now x plus y squared here is going to equal, let's put some equal signs here. I'll let you follow my work. Okay, x plus y times, x squared plus xy plus y squared. Okay, now remember, in this case, we can't really follow the FOIL kind of method, but again, we're basically doing the same idea. We're applying distributive property. We're going to multiply every single term times every single term. All right, so when doing that, let's see here, we're going to get x cubed plus a x squared y plus a xy squared plus a, let's see here, that's going to be a y x squared plus a xy squared plus a y cubed. So you can see already that's providing you a lot of terms here. And now what happens is, now let's go and look for the like terms. Now again, for like terms, we're looking for the same base and same power. So we're looking for an x squared and a y. Is there any other x squared? Yeah, it's not in the same order, but they're there. And an x and a y squared, you can see, is right there. So now when I go ahead and combine my like terms here, I get an x cubed plus a x squared y plus a y x squared, nope, sorry, plus an xy squared plus y cubed. Okay. All right, I'm going to do E over here for obvious reasons. I kind of ran out of some space, but then I'm going to put the answer back over there so we can kind of identify a little pattern that's going on. All right, so for E, if I was going to have, x plus 4, I'm sorry, y, x plus y to the 4th power, what I went over with students is, again, let's kind of do that trick, not really trick, but let's kind of simplify that a little bit as far as x plus y squared times x plus y squared, because really we can only multiply things at one time, two things, x times y as one time. And the really important thing that I want that I also wanted them to come away with this is understanding multiplication as far as area. When I multiply 3 times 4, that gives us 12. Well, geometrically, we can represent that as 3 rows times 4 columns. And when you have 3 rows times 4 columns, that gives you 12 boxes, right? And that's what area is. That's when we multiply length times width, we're getting area. So anytime we're multiplying, 2 terms or 2 quantities, we're going to be finding the area of some rectangle where those 2 quantities represent the length and the width. So you can see this is exactly what we're doing here. We basically have this quantity times that other quantity. So you could do distributive property like I did here. But again, if you think about this, this is now going to become a trinomial times a trinomial. And did I do 2x? Oh my God, I forgot to do 2xy. Oh, shoot. Okay. So let's go back and fix our answers because I was talking. Remember, you're combining your like terms, right? So that's a positive 2xy plus y squared. You combining those. And this is very, very important for us to understand. These 2 terms are the same, so there's 2 of them, right? So that's going to change, obviously, all my answers there. So that becomes a 2xy. So what happens is, so this was a, let's see, that's a, this becomes an xy squared, or this is a 2xy. So yeah, so that should have been a 2. Okay, and that would have been a xy squared. That's fine. And then this should have been a 2 times a y, so that would have been 2. Okay, and the reason why and I can't believe I actually didn't figure that out because I've done this problem 4 times already. That should have been a 3, and that would have been 3. And this is going to be really important when we'll come back to this later. So obviously we're going to come back to those as well. But again, when you combine like terms, 2x squared plus, an xy squared is obviously 3x squared. All right, but thankfully I caught that before I got too bad. So that's a x squared times a 2xy plus y squared times a x squared plus 2xy plus y squared. Okay. Now again, if you were to do the distributive property here, you can see how crazy that would be, right? It's like everything is going to be going everywhere. So what we can do is we can represent this as a box. And the nice thing about using the box method is since each quantity has 3 terms, I can use that. I can represent that with 3 rows. And then since this quantity has three terms, I can use this as 3 columns. So now all I'm going to do is put each term. So I'm going to have an x squared. Let's see, this would be a 2xy, and this would be a y squared. And therefore, this would be an x squared plus a 2xy plus a y squared. Okay, so now all you're doing is you're just multiplying the length and width times each one of those little boxes, and that's going to give you the total area or the product. And obviously it works too because everything is multiplied by everything, right? And that's what's important. This x squared gets multiplied by each and every one of those terms. So let's go ahead and do this real quick. X times x is x to the 4th. 2xy times x squared is 2x cubed. X squared times y squared is x squared, y squared. This becomes a 2x cubed, y. This one becomes a 4xy. No, that's wrong. That's a 4x squared, y squared. Right? X times x is x squared, y squared. And then this becomes a 2xy cubed. Over here, this is going to be a x squared, y squared. This would be a 4xy cubed. And then over here is going to be a y to the 4th. Now, I have everything kind of written small. I wish I would have done probably a bigger box. But the nice thing that I want you to understand here, and I'm actually going to use a different color to really show you this, is that the terms on the diagonals are like terms, right? You can see these both have an x cubed y, these both have x squareds and y squareds, and these both have an x and a y cubed. So when we're combining like terms, rather than like trying to like figure out, where they are and what they're like terms with, the easy thing to do here is just to go and look on the diagonal to combine like terms. So my final answer for E is going to be, I'll write it out one more time here and then I'll combine let's write it out. So am I even have room? I'm not. It's a big answer. So my final answer for E is going to be x to the 4th let's see, 2x cubed y is going to be a 4x cubed y. Then it's going to be a plus a 6x squared y squared. And then a plus a, something's wrong, that's not a 4, that should have been a 2. Right? And y squared times 2xy should have been a 2x squared. So therefore, that gives you a 4xy and plus a y to the 4th. Okay, so the only reason why I kind of went through all of this is was obviously to, let's just get rid of that e. You guys can see that answer is right there. Okay. Now, the reason why I kind of went through this is because I wanted students to kind of see this relationship with the powers. And, just to kind of cut to the chase, obviously, we noticed that the first term, a couple things that students always came up with, is that whatever the binomial expanded to, that was always the highest power, right? That's what the power that we started to. And it's also the power that we ended with. The first term always started at that power and then went in descending order, whereas the second term, the y, wasn't there, but then it increased to 2. Now, a better way to sometimes visualize this is we could think about this as like x to the 0 and 1, and then you could even put a y to the 0 here, right? Because y to the 0, anything to the 0 is just 1. But you can see here that if I put a 1 in for the x and the y, and that was supposed to be cubed. Geez, I'm writing all these answers wrong. But you can see the x, the first term, starts at 4, right? Because that was the binomial expansion, and then it goes in descending order. Whereas the second term starts at 0 and goes in ascending order, all right? So that was one of our main kind of points we wanted to take a look at. And those are kind of some of the patterns we looked at. We also noticed that the sum of all the powers was the same as the binomial expansion. We also noted that there's always one more term more. So therefore, if this is expanded to the 4th power, then that means there's 5 terms. This is going to have 4 terms, 3 terms, 2 terms, etc. And then the last thing that I really wanted students to look at was the, let's see here, was the coefficients of those numbers. But actually, let's come back to that in a second. So we did that. And then we kind of looked at the binomial theorem, and here's kind of a math way. But at least the way that this binomial theorem is written, we don't understand how A, B, C, and D came from. And so you look at that, like we get the powers, like I think you can understand the powers in that relationship, but like, understanding why, 4 and 6 and 4, like how do we know what that's going to be for x plus y to the 5th, right? And again, why do we have those numbers? Why do these numbers like even exist? Well, again, these numbers exist because we're combining like terms, right? So we know they have to be there. And that's why obviously that was obviously wrong, because when you combine xy plus yx, you're going to have 2 of them. So we have to have that 2 there. So to look at the kind of relationship, what we did is let's take out, these coefficients and let's put them under each other and see if there's any pattern that I can see, because we found the pattern with the powers, but we didn't see any pattern with the coefficients until we kind of take them out. And then we kind of see that, each of them always started with 1 and ended with 1. They also were kind of like symmetrical, like they repeated themselves. The second term, or the second to last term, was always the same as the binomial expansion, right? This is x plus y cubed, and then you could see that's to the 3rd power. To the 4th is right there. So those are some kind of the patterns that we found. And that was really the creation of the next part, which is Pascal's triangle. And so obviously we don't really get into depth as far as the Pascal triangle or get into combinations and that kind of understanding. We just really wanted to kind of look at this relationship of Pascal's triangle just based on the coefficients. And I only went up to n is equal to 5, but obviously when we do more problems, we're going to get a little bit more advanced. So, so then we just kind of talked about those patterns, but then we looked at another problem. And this problem was, well, if we understand that, right, we understand that Pascal's triangle and the behavior, what is that going to do for this? And so I wanted students to see about if they could maybe guess what the binomial expansion would be with this one and see how close they can get. And therefore, what I wanted to do is give them some time to try it, just doing the binomial expansion. And then while they're doing that, I was actually going to multiply it out to I was going to multiply it out and see if they got the same answer. Now, in this case, I don't know what one of them squared is, so therefore I'm just going to multiply, these two together first, and then I'll multiply by the third one. So here I'm going to have, let's see, a 4x squared minus a 2xy minus a y times 2x plus a y squared. So therefore, that's going to be, so it's multiplied times 2x minus y. That can be simplified to a 4x squared. Let's see, that's going to be a minus 4xy. Oops. Plus y squared. 2x minus y. All right, now let's go ahead and multiply this again. This looks like it's not going to be that fun to multiply via distributive property. So what I'm going to do is I'm going to do box method. I'm going to have a little bit more room, so I'm going to create at least a bigger box here. So I have a 2x negative y, 4x squared minus a 4xy, and plus a y squared. All right, so multiply that. That gives me 8x cubed. Length times width here, this is going to be a negative 8x squared y. And this would give me a 2xy squared. Now I'm going to do this height and all of these widths. So this would be a negative 4yx squared. This gives me a positive 4xy squared. And this is going to give me a negative y cubed. And again, look on the diagonals. Those should be like terms, which in this case, again, they are. So therefore, this final answer is going to be a 8x cubed. Let's see here, plus 32x squared y plus 6xy squared plus a y cubed. Okay, so the interesting thing here, and what I know something, yeah, okay. So the interesting thing here that I wanted to see is the coefficients no longer have those patterns that we looked at, right? They follow the patterns of the exponents, right? That works out, but the coefficients are not the same. So then we look at this and we say, why did it happen like that? Why do we not have the exact same coefficients going on here? Well, the reason why that happened is because now my terms have coefficients, right? I have a coefficient of 2 and I have a coefficient of, this negative 1. So now things are, oh, did I get that? Did I multiply those? What am I doing? I'm like crazy. Okay, that's 8x. I was wondering, I'm like, how am I getting, sorry about that. It's like I'm explaining this, I'm like, that's not the right answer. Okay, you're not multiplying these on the diagonal. You're just combining like terms. Wow. Okay, I'm not sure what I am doing here. That's 8x cubed. This becomes a negative 12x squared y. This becomes a positive 6xy squared. And this is a negative y cubed. Okay. But again, still the same idea. But you notice now we have a negative and a positive. Like, why do we have different terms? Well, obviously, that makes sense because now we have two terms that have coefficients in here. And again, another way that I like to write this out, if you're to do the binomial expansion, is I tell the students to put them in coefficients. Okay? So now, basically, what you can go ahead and see is this x has a coefficient of 2 and the y has a coefficient of negative 1. So it's not always just going to be these numbers, but these are basically like a scalar that we're going to apply. So then I kind of went through these two examples with the students, and the way that I kind of like to teach this is, first just kind of doing the binomial expansion with the powers. So taking the first term, raising to that power, taking the second term, putting it to 0. And basically I just kind of follow that method until we get all the way down, until we get the first term all the way down to 0. So that's going to be x is 0, and then this would be x cubed, y to the second, plus x squared, y cubed, plus x to the first, y to the fourth, and then plus x to 0, y to the fifth. Okay? And now we just need to take the coefficients from Pascal's triangle. Now, obviously, we could always go back and refer to what Pascal's triangle is up here. Hopefully, you see that it's 1, 5, 10, 10, 5, 1. But, the one thing I guess I also forgot to mention, when we look at Pascal's triangle, the other patterns that we recognized here is if we want to create this on our own, we can see that, 1 plus 4 gives us 5. 4 plus 6 gives us 10. So all we got to do is add those two terms to get the term below it. Okay, so when I want to find the next row, like I can create Pascal's triangle, rather easily on my own. The way that I, mostly remind students to do it is, create the one triangle, okay? And again, remember that the second term tells you what the expansion is, right? N of 2 is that second term. N equals 3, which is to the third power, is that 3. Raised to the fourth power, there's the 4. So you can see where all those values, come in. And so now I can just go through 1, this is going to be 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and then 1, 5, which is n is equal to 5, right? I know that expansion, 10, 10, 5, 1. And there we go. So those are going to be my coefficients. Now I'm going to use a different color here. I'm going to use red here because those basically, even though those are the coefficients, remember you're multiplying them because they're not always going to be just the numbers there. And that's what was the whole purpose of doing that last example. So you can see that you just can't like do the expansion and throw the numbers in there and say that's it because they are scalars. You're multiplying each of these terms by there. All right, so now let's go and simplify our answer. So we'll have a x to the 5th plus a 5x to the 4th y plus 10x cubed y plus a 10x squared y cubed plus a 5xy to the 4th plus a y to the 5th. Now again, these exponents showed up there because obviously each of my coefficients only had, or each of my terms, x and y, only had a coefficient of 1. So now let's go ahead and work into the next example that I did. Now, in this example, remember what I told my students was I want these to be 2x, and then that's going to be plus a negative y to the 5th. Okay. Okay. 2xy to the 5th. So now let's go ahead and write everything up there. So I have 2x to the 5th, and then this is going to be a negative y to the 0, plus 2x to the 4th, let's give them a little more space. Let's do this actually. All right, so my first term is 2x to the 5th, and then that's negative y to the 0. You don't really need to write that first term like that. I always just like to include it though, just for kind of like accounting purposes, and then also just to kind of make sure that, so at least when I'm teaching, you guys can see where that term is coming from. All right, and then that's going to be a 2x cubed times negative y squared plus a 2x to the 2nd times negative y cubed plus a 2x to the 1st times negative y to the 4th, and then last but not least a 2x to the 0 and a negative y to the 5th. Okay, but again, so that is basically taking your first term and your last term, going down in those ascending and descending order. Now we basically just need to take my coefficients, which I have in blue up there, and then just go ahead and write those in there. Okay, so I have 2x to 2x to the 5th here is going to be 2x. So remember, oh, and the other important thing is it's really important to use parentheses because, remember 2x to the 5th is not the same thing as 2 times x to the 5th, right? 2x to the 5th is 2x times 2x times 2x times 2x times 2x, where 2x to the 5th is 2 times x times x times x times x times x. So make sure you kind of understand the difference there. So this ends up being a 32 x to the 5th. Obviously, anything going to the 0 power, or anything to 0 power is just 1. Plus here, let's see, that's going to be a 16 x to the 4th times a negative y. Plus that's going to be a 8, oops, jeez. Why do I keep on forgetting? I did the blue I'm getting ahead of myself. I did the blue because we got to use these coefficients, right? So you got to multiply each of these terms by the coefficients. Now we should have 1, 2, 3, 4, 5, 6, 6 terms. 1, 2, 3, 4, 5, 6, which we do. Okay, so we do 1. I need to multiply this by 5, multiply this by 10, 10, 5, and 1. Let's just put a 1 there. Okay, now let's go ahead and change the colors. And go ahead and fix that. Okay, so now 2x squared is going to be a 32x to the 5th times 1. You know, it's obviously not change anything. And then plus, this is now going to be a 5 times 8x to the 4th times a negative y. Plus, we'll have a 10 times a 8x cubed times a negative y squared. So negative y times negative y is a positive y squared. Let's see, that's going to be a plus, plus a 10. So 2x squared is going to be a 4x squared. This becomes a negative y cubed, which is going to be a negative y cubed, plus a 5 times 2x times y to the 4th. And then that's going to be a plus a negative y to the 5th. All right, so now let's go and simplify here. So that becomes 32x to the 5th, 5 times 8, that's not right, that's a 16. 2x to the 4th is 16. Okay, so 5 times 16 is going to be 80, and times the negative y is going to be a negative 80. So therefore, that's going to be that's to the 5th power, because my 5s are tough. So it's a negative 80 x to the 4th. 10 times 8 is going to be a positive 80, and then x cubed, y cubed. Positive 80, x cubed, y squared, sorry. This becomes a 10 times 4, which is 40, but then again, we're multiplying by this negative 1. So it's going to be a negative 40, x squared, y cubed. This becomes a 10 x, y to the 4th, and then minus a y to the 5th. Okay? So these are the examples that I worked through. Okay, so now let's go ahead and get into the examples that we went over in class. So these are what I gave to the students. And then what I'll do is I'm just going to kind of work through these examples kind of rather quickly, you know, now that we kind of went through at least that process. So in this case, I just have x plus 7. Oops, I'm sorry. Okay, so this term then was just going to be, oh no, did I forget that? I did. Okay. All right, so looking at this one to the 7th power, it's a little bit higher. Not as fun. But again, we're just going to kind of start with the same thing here. We're going to start with x to, come on, x to the 7th. And then plus that's going to be x to the 6th y plus x to the 5th y squared plus x to the 4th y cubed plus x squared y to the 4th plus x to the 1st y to the 5th, and then x to the 0, which we don't really need to do, and then we'll just do y to the 6th, right? Because I don't really need to do this y, x to the 0. Okay, and now we just need to know the coefficients. And again, if we kind of go back, we create this Pascal's triangle rather quickly. We're just looking for where the second term is going to be 7. So just 1, 2, 1, 1, 3, 3, 1, 4, 6. That's the 4th expansion. Here is the 5th expansion. Here's the 6th expansion. So here's the 7th expansion. Okay, so I kind of ran out of space, obviously, but hopefully you can kind of see right there. And then now we're just going to take these terms and then plug them in as our coefficients. So therefore, that's a 1 as that coefficient. So let's do like a 1 times here. This is going to be a 7. We'll have a 21, a 35, a 35, a 21. Uh-oh, where did I miss here? Oh, I forgot to do an x cubed, right? So I'm missing a term. Okay, so that should have been a 35x cubed y to the 4th. And then that would have been a plus a 21x squared. I was wondering why that y to the 5th. Plus a 7x to the 1st, y to the 4th. And then plus a y to the 7th. It's a lot of writing and a lot of algebra if you haven't already noticed. Jeez. Okay, and then we can just, obviously, guys, just go ahead and simplify this. But this is basically already in kind of simplified form, so I'm just going to kind of roll with that. I'm going to do b just kind of down below it. And you don't need to do this. I always kind of like to put them in order like this. Just so therefore I can kind of see how things are. Now, in this one, I'm actually going to work out a little bit just because, you know, when you're using parentheses, there's going to be some differences here. Remember, anytime you take a negative term, raise it to an even power, that's now going to be positive. And anytime you take a negative and you raise it to an odd power, a negative number or term, that's always going to be negative. Now, the nice thing about this here is my second term, 1, like, it doesn't matter if this is, you know, 1 squared, 1 cubed. Like, I'm just going to kind of work without the ones, and I'll show you, like, why it doesn't really matter. So we'll just keep on going, like negative x. So if you see a 1 there, or a positive 1, usually it's like going to be kind of cool here to 0. And obviously that'd be to the 0, which would be that, you know, same term. But again, you follow this pattern. Now, again, if I had like 1, like it doesn't matter, like is what? 1 to the 0, like 1 squared times 1 cubed, like 1 to the 4th, like it doesn't matter. You're multiplying by 1. Each and every one of these terms are not going to change. Now, the only thing that does change, though, is the term of the signs of each of these, right? Because negative x raised to the 6 is a positive x to the 6th. Negative x to the 5th is a negative x to the 5th. So you can see that now we're going to have alternate signs. I don't know why I'm like having trouble today. So we're going to have these alternate signs. So that's the kind of important thing that I want you to kind of take away from this. And boom. And there you go. That is the expansion. So having that 1, you can see how that kind of quickly made this problem go by a little bit quicker. All right, now we just have kind of just 2 more examples here. Here we have a 2x and a negative 1. So again, to the 5th power. So I'm just going to rewrite this as a 2x to the 5th plus a negative 1. Oops, why am I writing to the 5th? I don't care about that. Okay, so now in this case, I am going to include that negative. You are going to want to make sure you include that negative 1. And since this one's a little bit shorter, I'm just going to include all, I'm just going to do all the terms. So I'll just do 2x to the 5th, negative 1 to the 0, even though we know that's 1, it's not going to impact anything. And then we'll have 2x to the 4th times negative 1 to the 1st plus the 2x cubed times negative 1 squared plus a 2x squared times negative 1 cubed plus a 2x to the first times a negative 1 to the fourth, and then plus a 2x to the 0 times a negative 1 to the fifth. Okay, but again, making sure that you include this negative 1 here is very important because it's a negative 1. So it's going to be, again, changing the signs. Now, we need to go back and recognize our coefficients here from Pascal's triangle. So the fifth term is going to be 1, 5, 10, 10, 5, 1. So I think I kind of hopefully can have that memorized here. So let's go ahead and boop, put it in blue. So that's going to be 1, 5, 10, 10, 5, 1. Okay. And just again, double check that. You can have Pascal's triangle with you, or at least for my test, I don't really care if the students memorize it because they can quickly create it, on your own. Or at least you should be able to quickly create it on your own. So now let's go and take a look at now let's just go ahead and expand this out. So 2x to the fifth, again, is 2x times 2x times 2x, 2x times 2x times 2x times 2x times 2x, which is going to be a 32, x to the fifth. That's obviously negative 1 to 0 is just 1, so we don't really care from there. This is now going to be a negative, so instead of a positive, this is going to be 2x to the fourth, which is again going to be 16 times 5 is 80, but again, it's going to be times a negative 1, so that's a negative 80 x to the fourth. This becomes a 8x cubed times 10 times positive, so that's going to be a positive 80x cubed. This becomes a 4 times 10, so that's a negative 40x squared. And this was going to be 4, that's going to be a 10 plus a 10, x to, don't forget the x squared. Yeah, 10x, and this would be minus 1. So again, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, I got 6 terms. So there you go. You can see how that expansion, kind of works. And again, you could break that down just for kind of sake purposes. I just kind of did a little bit more in this in my head. And then also you can see that this is very similar to our problem that we already did for the, 2x minus y. Instead of y, I'm just using 1, right? And that's really the only difference there. All right, so let's go ahead and do this one, this y, 1 minus 2x to the fourth. And again, if I wanted to rewrite that, I could rewrite this as a negative 2x squared plus 1. Why do I keep on squaring that? I'm not sure. Okay, so that's now going to be to the fourth power. All right, so again, just following our patterns here, this is going to be a negative 2x to the fourth power times 1 to the 0 plus a negative 2x times 1 squared. Now again, we see that 1 is the second term, so I'm not going to, we don't need to include this anymore, right? It's not going to matter if it's 1 squared times 1 squared, 1 cubed. So let's just do, the 2's here. Negative 2x squared plus negative 2x to the first, and then plus a negative 2x to the 0. Now again, I'm leaving a little bit of space again, remember, because I need these coefficients, right? To the fourth expansion is 1, 4, 6, 4, 1. So we just want to make sure that we give ourselves enough room here to be able to add those back in. So we have 1 times 4, 6, 4 times 1. Okay, and again, just want to make sure that I had that going correct. 1, 6, 4, 6, 4. Sweet. So now let's just go ahead and simplify that actually. I don't know why I took that away. All right. So we go ahead and simplify this now. So 2x to the fourth is going to be 16. So that's a positive 16. X to the fourth. Plus, this becomes now a negative, right? So this is a negative 8x cubed times 4. So that's going to be a negative 32x cubed. This is positive. Anything negative squared is going to be positive. So that's going to be a 4 times 6. So that's going to be a positive 24x squared. This becomes a negative 8x. And this would be a plus 1. right? Because even though that's a negative, you're raising to the 0, which is going to be 1. So 1 times, the 1 is obviously just 1. And there you go. All right, so now one of the things that we also, kind of look into is just looking at the third term. Like you can see this expansion is pretty in depth, right? There's a lot of work that we're kind of showing here for each of these problems. And so one of the ways that we can kind of make this a little bit easier is rather than trying to find the whole expansion is just find the third term. Now, obviously, once you know about combinations and all that, combinatorics, then you can be able to do this a little bit easier than what we're doing. But at least in our class, we're just going to kind of work on, understanding that relationship of the Pascal's triangle as well as the expansion just to be able to figure out those terms. So I do know there's other ways to work on it, but those are the ways we just don't get into this class. And obviously trying to keep my students focused on what we're learning, then I just continue with the way that we've been doing the problems. So if we wanted to figure out So it's asking us to find the third term. The nice thing is we don't need to find the whole expansion. Like if we're looking for the third term, like that's the first term, second, third term, fourth term, fifth term, right? There's always one more term than the expansion. So since this is, negative x minus 3 to the 7th, we know there's 8 terms. So the third term is going to be the third one in from the left, all right? So basically, all we simply need to do is just do our relationship, negative x, plus a negative 3. All we need to do is do this relationship, but only to the third term in. So if we were to kind of do it like we're normally doing, negative x to the 7th, negative 3 to the 0. That's the first term. This would be the second term. And then this would be the third term. Okay? So that's very important here. So now we know that's the third term. Now we just need to look at the coefficients. Now, for the sake of time, I'm only going to expand off the third term here from here. So again, if I wanted to find that third for the 7th term, actually, I'm sorry, the 7th term in the expansion is going to be 21, right? You can see the 7, that's this, when n is equal to 1. So therefore, we'll just write a 21 in there. Now, I already forgot what that second term is. I don't need to know what that second term is, though. I just need to know there's a 21 there, right? Because we're only looking for the third term. I just did what the first and the second term was just so I could practice getting myself to that third term. Now let's figure out everything is going to be. So 21 is just 21 times negative x to the 5th is going to be negative x to the 5th. And then negative 3 squared is going to be 9. All right. Now, 9 times negative 1 is going to be negative 9. Negative 9 times 2 would be a negative 18. Negative 9 times 20 would be a negative 180. And then negative 9 times 1 extra 9 here is going to be a negative 189x to the 5th. And there you go. So now let's go ahead and work on just a couple more of these problems. Same kind of one here. Now, this one's to the 7th power, right? So if you kind of think the powers are going to be exactly kind of the same. It starts from the 7th, so the third term is going to be 6 to the 5th. So I should have this as x to the 5th, and then my second term is negative 1 to the 0, 1 second power, right? Just like it was negative 3 in the last example. And then I should have a 21 in front. So therefore, this is going to be, that's a positive, so it should be a 21 x to the 5th. Okay, so since that was to the same powers, that's why that's why the 21's there. And then again, I'm using this as a negative 1 because I'm writing this as x plus a negative 1 to the 7th. And that makes sure that's very important because you can see how I'm getting a positive here because that negative 1 gets squared. All right, so to the 6th power, well, again, if we start, the first term was at 6, the second term, so again, like if I start at 2x to the 6th, 1 to the 0, that means the second term is going to be 2x to the 5th, y to the 1st, and hopefully you're trying to getting this pattern here. So this one is going to be 2x now to the 4th, and that's not a 1, that's a y. I don't know why I'm doing that. Y squared, right? So each and every term, you can see that second term is always being y squared. So 4x cubed, oh, I'm sorry, and this is the third term. Now this is to the third term to the 6th expansion. So it's not 21 anymore. Let's see what that is. 6th expansion, third term is 15. So that's going to be a 15. All right, so 2x to the 4th So 2x to the 4th is going to be 16. So that's going to be a 15 times a 16, x to the 4th. Obviously then times 1. Now 15 times 15 is 225. So if you add an extra 15, right, because you have one more, that should be 240 x to the 4th. And actually, I didn't work that one out. Let's just make sure I'm doing my math correct. 240 x to the 4th. There you go. All right, the next one here, this one is going to be a negative x plus a negative 2. Ugh, nobody likes this one. All right, so the first term should be 5, 4, 3. So that's going to be negative x to the 3rd power, and that should be a negative 2 to the 2nd power. Into the 5th expansion, the coefficient of the 5th expansion is going to be 10. So let's put a 10 in there, and now let's go ahead and simplify that. So that's going to be negative x cubed times a positive 4. And therefore, when we multiply this all out, we get a negative 40x cubed. All right, and then last but not least here, again, we have a 3x plus a 2 to the 4th. Okay, so the third term before 3, 2. So this will be 3x squared. Second term is obviously, or third term again, is going to be a 2 squared. And then of the 4th expansion, I'm not sure what that is. Third term of 4th expansion is going to be 6. Okay, so I have a 6 times a 9x squared times a 4. Okay, so let's see here. So 9 times 6 is 54. 54 times 2 is 108. So and 108 times 2 would be 216, right? So times 2 is the same thing as multiplying by 4. So let's do 216x squared. And just to make sure that I'm not making a mistake on a video. Yep, 216. There you go. All right, sweet. Now, did I just do all those in the same one? I did. Awesome. So I don't need these slides. Cool. Okay, so we did all this practice, and once students kind of get some practice with that, they feel pretty comfortable. But then the main thing is I wanted to kind of say, well how is binomial, like obviously multiplying binomials is helpful, right? Because nobody really wants to multiply binomials all the time. So why is this really going to be, that beneficial? How else can we use this? And we don't really need to go far. Here's from looking back at vertex form. And so vertex form is very nice because when we had problems that were in this format, we could easily identify the vertex. And so hopefully you remember that vertex form is y equals a times x minus h squared plus k. Okay, so the vertex was h comma k. Now you could also find the x-intercepts of this as well as the y-intercepts, and that's hopefully something that we've identified as well as the transformations. So those are some things that we've practiced with vertex form. But remember, getting into this polynomials unit, which a quadratic is, a lot of times we talk about, finding, the zeros and the multiplicity. And I wanted to cover these problems because I want students to really understand, how we can identify that or how this is beneficial, but also how this is not beneficial. Like what we previously learned, how that's helpful to compare to, different forms of polynomials and how that can be beneficial. So the one thing we want to remember is, linear factorization. So that is kind of like the new form that we worked on with polynomials. When we have something in y is equal to, x minus c1 and times x minus c2, then x equals c1 is a 0 and x equals c2 is a 0. Okay, because you set those equal to 0, you apply the zero product property, and so on and so forth. The important thing is this vertex form is not in factored form. So a lot of times when I say, what are the zeros? Students look at this and say, oh, the 0 is 3 with a multiplicity of 2, because they're thinking of a problem that looked like this, 3 squared times like x, minus 4. They're like, oh, zeros are 4 and 3, multiplicity 2, multiplicity 1. Well, yeah, when it's in factored form. This is not in factored form. So let's go ahead and identify all these parts, and we'll kind of see why that doesn't make any sense. So first of all, vertex is 3 comma negative 4. And the transformations are going to be, right 3, down 4. I wanted to review with the students. And then the or the zeros, well, again, zeros are just like finding the x-intercepts or the real x-intercepts. So we set this equal to 0, and then we say x minus 3, squared minus 4. Then students got 4 over there. And then they were supposed to take the square root of both sides, and then they had to include plus or minus 2. And then when they got x is equal to 3 plus or minus 2, and we got the zeros to be 5 and negative 2. I'm sorry, 5 and 1, right? So those were where the graph crosses the x-axis, which makes sense. We should know there are only going to be 2 x-intercepts here. But there's not one x-intercept with the multiplicity of 2, because remember, the multiplicity tells us the behavior of that. So I use this as a review in my lesson. And so that was the zeros. Now the problem with this is, we know what the zeros are. We don't know what the multiplicity is because it's not in that factored form. So what I'm going to do is I'm going to use the graph to understand the multiplicity. Before I do that, let's go ahead and find the y-intercept real quick. The y-intercept is when x is equal to 0. Okay, and so what we get here is you should get a 5. So when I go and graph this, okay, I know it has a vertex of 3, negative 4. X-intercept, or an x-intercept at 1, x-intercept at 5, and a y-intercept to at 5. Okay, so, you know, there's the graph of the quadratic. And it's just important for students to see that, yeah, those zeros, when you set equal to 0 and you solve and you use plus or minus, you see that there are 2 x-intercepts. Now they cross like a line. So again, that's telling us our multiplicity here is 1. And also your multiplicity of each 0 should add up to the power. That was something that we looked at and when it was in factored form. Like this is equal to some polynomial to the 3rd power because your multiplicities add up to 3. Right? So we have 2 x-intercepts or 2 zeros, their multiplicity should both be 1. Okay, so just be careful when you see a binomial squared. If it's not in factored form, you can't identify the vertex, or I'm sorry, the zeros in the multiplicity from that case. However, in this case, you can see that this is just a factor. Like it's not, even though it's not multiplied by another factor, you just have an isolated factor. It's not being separated by addition or subtraction. So this one actually is at a 0, does have a 0 at 4 with a multiplicity of 2. Now let's see why this one looks differently than this one. So what I did is, say, all right, well, again, the vertex here is, 4 comma 0, right? Because you could always just put a 0 there. Let's do the transformations here. So this is right 4, vertical stretch of 2, and we have to reflect the x-axis. Okay, so we reflect the x-axis, and so let's go and find the zeros. Now let's pretend we don't know what the zeros are, and let's just use our definition here. 0 is equal to negative 2, x minus 4 squared. Now again, one thing that students again still kind of get confused is they say, oh, well, negative 2 is a 0. Well, no, because if you try to solve for x, right, that's the zeros when you're solving for x. The first thing you're going to do is divide by negative 2 anyways, and you're going to see negative 2 is going to go bye-bye. So negative 2 is not a 0, right? Take the square root, can't take the plus or minus square root of 0, so that's going to leave you just with x minus 4. So x equals 4. X equals 4 is the only 0. Negative 2 is not a 0, only just 4. And you can see again the power of that factor is 2, so the multiplicity is equal to 2. And then the y-intercept, we're just going to have y is equal to negative 2 times 0 minus 4 squared. So negative 4 squared is positive 16. 16 times negative 2 is a negative 32. Okay, so this graph, let's graph this graph, is 1, 2, 3, 4. There's my 0 or my x-intercept. It opens down, right? And so it's going to look something like that. So you can see now, oh, it does make sense that it has 1, 0 and a multiplicity of 2, right? Because it bounces like a parabola. So I wanted to kind of cover this because obviously we spent a lot of time in the last lesson learning about multiplicity and zeros and finding that's a very important part. But also, going back to quadratics or having the binomial squared is very helpful for us to be able to identify the transformations as well as the vertex of a polynomial. Like here, it's not very obvious what the transformations or like a vertex of, that graph is going to be. So what I did is, or we looked at, basically my question is like, well, what if I had problems that looked like in this form? How would you find the vertex? Like this form just tells you, that's standard form. There is a formula for the vertex in standard form if you remember it. But what about like in factored form when it's written as linear factorization? like you can find the zeros really quickly, -2, -4, but what about at the vertex? Like what would you do in that case? So the process, what we're going to do is actually, did I do these two? I'm going to compare those two. So the process that we're actually going to complete here is completing the square. I thought I fixed those two though. I guess I did not. Let me see which problems. Okay, well, that's the same one, 2x plus 1. No, I guess not. Okay. I think just in class I changed it. I didn't change up here. So the process is completing the square. And basically what completing the square does is that creates a perfect square trinomial for us. So that's our goal. We're going to be creating a perfect square trinomial. That's it. I added that third one in there. So what is that? X plus 2, x plus 4. Okay. X. So I added this one in my lesson. I didn't change it in here. Y equals x plus 2 times x plus 4. Because I ask you, what do you do here? And students are like, oh, well, I don't know. And then, but I didn't cover this one problem either. So let's do this problem, and then I'll do that problem. Perfect. Okay, there we go. I forgot to change this slide. So we're going to complete the square. So basically what we're going to do is set parentheses around our first two terms, our quadratic and our linear term. We're going to take b divided by 2, which is going to create, are going to help us find the value c that completes the square. And therefore, we're going to add that term to the inside and the outside and then factor. So let's just kind of go through the process here. You can see that these two problems are down in my example below. But I wanted students to kind of think about these as they saw them to what we're going to get here. All right, so now in this case, I'm actually not going to complete the square in this first example because I don't need to. What I want you to recognize is when you see a trinomial, that this is a binomial squared, right? This is, I'm sorry, a perfect square trinomial. Perfect square trinomials can be factored into binomial squared. And that's the important thing about completing the square. That's what we're looking for. We're looking for perfect square trinomials. Now this next example, so again, here we're done. Now the vertex in this case is -1, 0. Button. Didn't even need to complete the square. That's nice, but that's really not going to happen again, okay? So the next example looks like it's a perfect square trinomial, but it's not, okay? Because you can't have the same terms multiplied to give you -1. So what we're going to need to do in this case is I will actually use my color code here. All right, we're going to group the quadratic and the linear term. So inside these parentheses, I want to create a perfect square trinomial just like this one, okay? It's not going to be the same, but I want to create the same type of one. So to do that, all I'm going to do is take my b divided by 2 and square it. Now some people remember like, what's b? ax squared plus bx plus c. I guess maybe I should write that, the ax squared and the bx. So we're going to group, we're going to take the b, which is -2, divided by 2, and we're going to square it. So -2 divided by 2 is -1, -1 squared is +1. Now, you got to make sure that you add that inside as well as outside of the parentheses. So let's go ahead and, the only thing I hate about this is I keep on going back and forth of my colors. So therefore this becomes a x squared minus a 2x, and then let's add the 1. Now it's very important that you understand by adding the 1, what you just did is you just created a perfect square trinomial. This original problem was not a perfect square trinomial, but when you took the middle term, divided it by 2 and squared it, you just created a perfect square trinomial. This is factorable, just like this problem, every single time. And that's the beauty of completing the square. However, we got to remember, we can't just like ignore that there was originally a -1 there. Like we need to keep that -1 there. We also can't ignore, to get this perfect square, we had to add the number 1. So what that means is then we need to subtract the number 1 to keep this in equation, right? You just can't like add, for instance, what I did in class, I said, 5 is equal to 5. But 5 does not equal 5 plus 1. Right? You just can't add a number to a side of an equation and make that equation still true. However, what you could do is take 5 plus 1 and minus 1, oops, and that does work. Okay, so now we have this that is, that can be factored, and that becomes, what is this factored form? That's going to be x minus 1 squared. Oops, sorry, not add 1. You got to subtract 1. I said it, but then I didn't do it. -1. So that'd be a -2. All right, and then the next example, or last example, here. Now this one is in factored form, so the best thing to do would actually be to multiply this out, right? And so therefore we get a y equals a x squared plus 6x, x squared plus 6x plus 8. Okay, so now my b squared is going to be a little bit different. Now my b is 6, so I'm going to take b divided by 2 and square, or 6 divided by 2. Divided by 2 is 3, 3 squared is 9. So I'm going to take that 9 and I'm going to add it inside my two parentheses. So I have x squared plus 6x plus 9, and then plus 8, right? You can't ignore the 8. And since you added a 9 inside the parentheses, you have to subtract a 9 outside the parentheses. Again, we created a perfect square trinomial, so therefore we're going to want to, we know that that is a perfect square trinomial that can now be factored down, and therefore 8 minus 9 is going to be a negative 1. Okay, so there you can see, again, how that works. All right, so then I just kind of gave the students, a couple more examples to kind of work on. And let's see, I forgot to write the vertex here. So in this case, the vertex is going to be 1, negative 2. Here, the vertex is negative 3, negative 1. All right, let's see if we can actually, I think I can actually complete the square. I think I might have enough room here. Let's see if I can do this. So this is going to be, my b squared is, let's see, it's 4 divided by 2 squared. So 4 divided by 2 is 2, 2 squared is 4. Okay, so that would give me y equals x squared plus 4x plus 4 plus 4 minus 4. Oh, this was already a perfect square trinomial, so I didn't really need to do anything with that. Why am I doing that? Why did I do that? Okay, well, oh, I know what I wanted to do. Okay, so it's kind of interesting instructional practice I did here. But hopefully before you get to completing the square, you recognize that this is a perfect square trinomial. So I don't even need to go through completing the square. I can just factor this into an x plus 2 squared, right? And that creates a perfect square trinomial. So again, what we're looking into is, I guess probably completing the square would be one way, but really the best thing is, create this as a binomial square to identify the vertex. So the vertex in this case is a negative 2, 0. Now in this case, my b is negative 4. So my b divided by 2 squared is going to be negative 2 divided by 2 squared, which is equals to 4. So let's group the first two terms. So y is equal to, x squared minus 4x plus 4 plus 5 minus 4. Now again, that is, this is a perfect square trinomial, so this can be factored down into an x minus 2 squared minus plus 1. Okay, so therefore the vertex now in this case is 2, 1. So what I was trying to get at was to students to be looking at that relationship, to be looking at that relationship of the perfect square trinomials. And you can see that obviously the purpose here is to, if we don't have a perfect square trinomial, then to create one. So in this next example, I identify that this is a perfect square trinomial, like x minus 3 times x minus 3. So I can just rewrite this as x minus 3 squared. So my vertex here is 3, 0. My vertex 0 is 2, 1. Okay. So in this case, now my b divided by 2 is going to be 6 divided by 2 squared, which is again equal to 9. So now I'm going to take that 9, I'm going to add it inside my parentheses as well as outside, and subtract it outside my parentheses. Now, this is a perfect square trinomial just like this one. The only difference is my middle term is positive, so therefore I'm going to have my two terms add, so that's going to be an x plus 3 times an x plus 3. Oops, well, let's just write that x plus 3 squared, save some time here. And that's going to be minus 10. So now my vertex here is a negative 3, negative 10. All right, last but not least one is the fractions. Now, before I get into the fractions, did I add the... Let's go and look into the fractions. Before I get into the fractions, do you notice any patterns that we could apply to any quadratic when we are, creating this perfect square trinomial, or trying to complete the square? And the one thing I wanted you to see is, like, what is the relationship between, like, this b divided by 2 and what our binomial squared is? And hopefully what you recognize is that the relationship is x is equal to plus or minus b divided by 2 squared. That binomial squared, I guess I should probably write that in there, is always x plus or minus b divided by 2 squared. Okay? So obviously if your b is positive, then you're going to have a positive binomial, right? That's not here. Here you can see my b is negative. My binomial squared is negative 2, right? And where did negative 2 come? It's really just b divided by 2. Negative 4 divided by 2, negative 4 divided by 2 is negative 2. However, here my b is positive, my binomial is positive. How do I go from, how to get 3? I just took 6 and divided it by 3. So therefore, if you want to use that logic, I should be able to understand that this is going to be y equals x plus 1/2, right? Because positive 1 divided by 2 is 1/2 squared. Now, I don't know what the rest of that's going to be, but let's just assume I know at least that's my binomial squared. And then this one, using that same understanding, should be x minus 1/2 squared. Okay? Now, again, I'm still going to kind of work through the problems because you're still going to do the same thing. You do the same process. I just wanted to give you an alternative method to be able to figure them out. So again, we just take your b divided by 2 and square it, which is 1/4. So y is equal to x squared plus x plus 1/4 minus 1/4. Oops, there's still a plus 1/4 there. Oh, let's just keep it there. Okay, so again, this actually is a perfect square trinomial. What two numbers, this one's kind of hard. People are like, I don't know how to factor this. Well, if you follow the patterns, you'll be okay. Like, what two numbers multiply to give you 1/4, add to give you 1? The answer is 1/2, positive 1/2. So this is x plus 1/2 squared, done, 0. So therefore my vertex is negative 1/2, comma 0. And then over here, we can really kind of go with that same thing. What we'd have is x squared, b divided by 2 is going to still be 1/4. It's a negative 1 divided by 2 squared, which is 1/4. So that'd be x squared minus x plus 1/4 minus 1/4 plus 1. So I'd have y is equal to, now again, this one is going to be the difference, it's negative, right? And then negative 1/4 plus 1 is, that's just going to be a positive 3/4. Okay, so there you go, ladies and gentlemen. That was basically what we did. It was just kind of an introduction. I know we can get obviously a lot more advanced in completing the square, but really what I wanted students to come away from this was understanding really this idea of completing the square, of creating a perfect square trinomial, and then also understanding that relationship. If you're having trouble factoring the perfect square trinomial, understanding how that relationship kind of works. Later in the year, we'll get into factoring out terms and stuff like that. But that was really about it. So then we just kind of went through a just kind of reflection on things that you felt well understood from the lesson and what you didn't understand. And if you guys have any questions you'd like to add to the comments below, feel free to add them, and I'd love to hear your thoughts as far as how this lesson went for you. I hope you guys have a good one, and I'll see you on the next one.